So my name is Stephane Houel. I work in the same group as Michael and Aaron. And today, my presentation fits perfectly after Aaron because what Aaron showed you is just like you can do a lot of characterization on the Q-Exactive platform. And now what I want to show you is just like sometimes you need to go one step further. So this is a picture from a Kuhn paper in 2009, and it shows you why sometime you will need to go to have a different mode of fragmentation. So when you do peptide mapping, you can use CID, HCD, and ETD, and you will get the answer you want. But when the question you ask is the site occupancy of your PTM, or sometimes the conjugation of your ADC. So the HCD will not provide you the answer. And also, Aaron showed you some data for middle down that you can get very good data, but the preferred mode of fragmentation for these type of assays will be ETD. So the presentation, I will have few case studies that will go through it and just show you what you can do. So Aaron showed on the, talk a lot about the Q-Exactive family. At Thermo, we also have another family, which is the Arbitrab fusion tribrid. And one of the major differences, on the Q-Exactive, you have the HCD, which is the best all-around mode of fragmentation. And on the tribrid, you have the HCD, you also have CID, ETD, ETHCD, ETCID, and you also have UVPD on non-commercial instrument. So all of the data I'm going to show you, they come from the Arbitrab fusion tribrid. So case study 1, Etanercept. And I'm going to look at O-glycosylation. So Etanercept is a fusion protein. There's 3 N-glycan sites, and there's 13 reporting O-glycosylation sites. So Etanercept is N-brail. It's expressed in CHO cells, so we know that the O-glycosylation will be a core 1. So now it could be core 1 with 1 or 2 sialic acid. So to remove some of the heterogeneity, first we're going to remove the sialic acid of the O-glycan, and after that we do trypsin digestion. And we're going to do peptide mapping. So I'm going to show you a result just for that peptide, just as an example of what you can get. So that peptide started at serine 186 and finished at the arginine 201. This is what you get after processing HCD data from BioPharma Finder. You get 4 peptides with core 1 tag, and you also get the peptide without any O-core glycan on it. What's also interesting is just you get 2 peptides with 2 different registration time here with 1 core 1 tag. So you already get a lot of information with HCD. Now if you have the question, which sites are occupied for each of them? We can start to look at it. Can we answer that question with HCD or CID? So the question is, I have 3 serine and threonine, so any of them could be occupied. When I have 1 core 1 glycan, which one is occupied? So this is the 1 core 1 glycan, and this is the CID and the HCD. And you have a decent fragmentation here. The problem that you have here is just when you do CID, the major fragment ions are actually loss of the O-core 1 or the loss of the galactose. And if you look specifically, you don't have any fragmentation between the serine and threonine here. So if any of these 2 are occupied, you won't be able to see which one is occupied. The same thing for HCD. You actually have a nice backbone fragmentation, but again, between the serine and threonine, you don't have any information. So now we're going to do ETD, and so we are short with the HCD and CID, but now we would like to do ETD. So for people who did ETD MS, just to have ETD on the mass spec, it's not enough. To get very good spectrum, you actually have to design the experiment when you do the acquisition. So this is the method I use to do, it's a DDA method. What's different here, I choose the scan priority depending on the charge state. So in that case, I say, if you see charge 5 or 7, do those one first. And then the reaction time you are going to use is 20 milliseconds. If you don't see any of those, just go to charge 4. But the reaction time is going to be different. I do this type of decision tree, and it's a very simple one, and it takes 2 minutes to make in the tune file. It's to optimize the spectrum I will get. So let's say you have an O-glycopeptide. You see the +2, the +3, and the +4. Even if the +4 is at 1%, I promise you, when you target the +4, you will get a better MS off of it, even if at low intensity. You could also do stuff a little bit more complicated if you want to. So in that example, for every charge state, I define a mass range, and when I do the DDA, I say first pick the highest charge state and the lowest M over Z. And in that case, I use the calibrated ETD reaction time. So you can define the one you want, or you could use what you did during your calibration with angiotensin. Also, people like to do HCD followed by ETD for every precursor. So in that case, I say you are going to take HCD, and on the same precursor, you are going to do ETD. Or sometime when Aaron showed you the 547 for the ADC, and you say, okay, when you see the 547 in the HCD MS2, take the same precursor and do ETD on it. And all of that can be done automatically. So now, if we go back to our core 1, just one core 1 tag on the peptide. So this is your ATD spectrum. Now actually this one is, I don't see very well from here. This one is the one with no core. This is the ATD spectrum, and if you zoom in, you have a beautiful fragmentation. And if you look at the coverage, you have excellent peptide coverage. So this is the one with no O core, and just like ATD spectrum is beautiful. So I just want to point it out here. You have a fragment at the N-terminal cell of the protein, and it's a Y13, which makes sense. So now if we look at, we got two glycopeptides with one core, one tag. One at 30.4 minutes and one at 31.17 minutes. And actually, we get, in that case, fragmentation between the serine and threonine. So here we start to the C8, and C8 are the same between the two. So we're almost sure that that serine is not occupied in these cases. So now we go to the Z2, and the Z2 in the lower one is here. In the other one, the delta mass between the two is 365.1307, which is the mass of the core. So right away, we know that in that case, the first threonine is occupied. Now we want to double check for the other one, and for the other one, we look at the C14, and the C14, it's again a delta mass of 365, so in that case, you know that that serine is occupied. So it's very straightforward. You actually don't need to have a lot of ions just to pinpoint where the fragmentation is, and you can do that with ETD very, very easily. And the data were acquired in DDA. I didn't do any targeted in that experiment. So now with the ETD spectra, we'll pinpoint the site of O-glycosylation. So now if we look at the one with 2 core 1 tag. So again, there's 3 sites. So you could have, if I call that A, B, and C, you could have AB, AC, or BC. So you have 3 possibilities, and you want to know which one, in that case, are occupied. So I look at the C5. The C5 is the mass of SMAPG. That means that serine is not occupied. Right away, I can tell you. And then if you look at the Z8, is actually the mass of that fragment ions with 2 core 1 tag on it. So you know those two are occupied in the core 1 too. So now the one with 3 core, so it's straightforward, but we still don't want to verify. And then if you look at the C1, it's the mass of the serine plus 365.1322. So we get all of the information we needed. And then as a confirmation, the Z3 is the mass of STOR plus 2 core 1 tag. So from the picture you had with the HCD, I was not able to pinpoint which one was occupied. So now after ETD and a simple DDA method, I was able to pinpoint. So in the XIC or all of those, I can pinpoint exactly which one is occupied. So that was for the PTM. So now still on Etanercept, we're going to look at disulfide bond. And on the tribrid, you have ETD, but you also have an ion trap which give you the possibility to do MSN. So how could you use it for characterization? So this is Etanercept, and I got a sample from a collaborator. I do the reduced peptide mapping, and on the N-terminal side of this protein, or this sample, I'm missing the LP. So this is the result of the peptide mapping, and I have all of those peptides. None of them contain the first 2 amino acids. So if you look at the sequence, actually, there's a cysteine here, so it's involved in disulfide bonds. And from the HCD, it suggests that these 3 peptides are linked together. So now I want to have very strong confirmation that this is the right one. So when you do ETD on disulfide bond peptides, you are going to have 3 fragment channels. You are going to create some peptide just by containing the disulfide bond. So you are going to chop one side or the other one, and you still have some disulfide bond. On the other spectrum, on the right side, you are going to have fragment ions. And in the middle, you're actually going to get your peptide by itself. So you are going to break those disulfide bonds, and you have peptide 1, peptide 2, and peptide 3 by themselves. So now if we isolate those MS2 ions, and we do the fragmentation MS3 HCD, what you should get, it's a pure spectra of each peptide that were involved in the disulfide bonds. So how does it work? So we do ETD in the dual pressure linear ion trap. Actually, we do in the high pressure cells. So you are going to do ETD in that part. You are going to use the ion trap to isolate the MS2 ions. And by sending that to the orbit trap, you are going to do HCD fragmentation in the ion routing multiple, and you are going to analyze that in the orbit trap. So even if it sounds complicated, actually, I did it in the targeted fashion. And the tune page is so well designed that it's very, very easy to do. So now if we look at the data, so those are the 3 peptides that are involved. And because there's a lot of ions, I try to color-coded them. So in blue is going to be the first ion. And if you look at the deconvoluted spectra, here it's the mass of this peptide 1 by itself. Here's the mass of the peptide 2 by itself. And here's the mass of the peptide 3 by itself. And the M over Z ions are those ones. So we're going to do, this is the MS2, and for the MS3, I'm going to trigger each of them one after the other one in my method. And if it works, I should get pure HCD spectra for any of them. So this is peptide 1. MS2 ETD of the 721, MS3 of the 1080. And this is the MSMS HCD that you get. And it's important to notice that on that peptide, you also have an O-glycan, and you get the oxonium ions at 204 and 366 that are there, and you get a very nice sequence coverage. So if people did disulfide bond mapping, usually when you look at the data manually, it's almost impossible, especially when you have 3 peptides linked together because you have fragments everywhere. Here you can do it manually very, very easily, and that was acquired in the orbit trap. Now if we look at the second peptide, this one is a little bit more difficult because to get that peptide by itself, you need to break the 2 disulfide bonds at the same time. So the intensity is a lot lower. So acquire the MS3, one in the orbit trap and one in the ion trap. At the beginning, when you look at it, you say, it's just like this peaks, but it's just the single two noises. I would like to get something better. So you do it in the ion trap, you get better sensitivity. But if you look at it, you actually get few more ions. But even in the ion trap, what you get was very, very nice. And you actually have very nice fragmentation. You have a lot of Y ions. So even in the case where this peptide would be a low intensity, when you do this MS2, MS3 technique, you get very nice and pure spectra for your disulfide bond peptide. And finally, the last one, it's a small one, and the MS3 HCD, you get almost complete sequence coverage on that peptide. So it was just to show you that ETD with an ion trap and the MSN could be very, very useful for characterization, and it could be used for in a lot of different occasions. So now, Aaron already talked a lot about ADCs, and I'm going to show you why ETD could be useful in some cases when you do antibody-drug conjugate. So Aaron showed you light chain 12 lysine, heavy chain 32 lysines. We're going to do peptide mapping, and I'm going to skip that one. And when you do it, you have a stereo center on the drug linker. So each peak, you will have the 547 that Aaron showed you, but it will come also as a doublet. So if you look at the number of lysine, we have one case here where we have 3 lysine. So you have the C-terminal lysine, but you have 2 more. And the idea was, it was coming from a customer, could you use ETD to pinpoint the site of conjugation? And I say, we can try. So this is the results from the HCD. So this is the non-conjugated peptide that eluted at 22 minutes, and you get your doublet eluted at 54 minutes. So now in that case, I'm going to park the quad on those specific ions. I want to get the highest quality MSMS. So this is what you get for the non-conjugated peptide. You get a beautiful, very high intensity Y ions, and if you look at the sequence coverage here, it's beautiful. Now if you look at the HCD spectrum, you get very nice sequence coverage too. But if you look at the most intense ions, at the one at the neutral loss from the drug linker, and you get nice fragmentation, but all of those at low intensity. So now what will happen if we do ETD on something like that? And the goal was to identify the site of conjugation. So here it's my peptide with 3 lysine, and I found the +5 and I did ETD on it. And I want to know which lysine is occupied. So I'm going to look between Z3 and Z4, and if it's conjugated at that one, the delta mass should be the lysine plus MCCDM1. So this is what you get, the Z3, this is the Z4, and you identify those fragment ions at 3 and 2 ppm, and if you look at the mass that you get, it's actually the mass of the lysine plus MCCDM1. So right away you can tell that that lysine was conjugated, and it was pretty straightforward. So now I want to sanity check. I want to look at the C14 and C17 and be sure that what I said is true. So this is the C14 and the C17, and even in the C17, you see you have some chimeric spectra. You have another fragment ions here, but with the resolution we have, it's not an issue just to find it. There's a +1 and a +2 together, but the one we're interested in is the nice 31, and it's at 2.2 ppm. And if we look at the delta mass, it's the lysine, the proline, and the glycine that are together. So we double check. We're sure that that was the first lysine that was conjugated. So now if we look at this little peptide, there's just like one lysine. So ETD will not, we don't need ETD to know which one is conjugated. But you get this doublet around like 55 minutes. And again, I use a targeted approach to get the highest quality MSMS I could get. And what you have, it's a lot of neutral loss. So this is your 547, that you know that it's a neutral loss from the linker drug. And the 911 is actually the complementary ions. These two are the most intense one, and actually you get just 1 fragment ions. So if you want to get more information on the backbone fragmentation, on the backbone of your peptide, you can use ETD, and actually, then now you get more intense fragment ions, and if you look at the two, you get complete sequence coverage between HCD and ETD. This is the power when you can mix the different mode of fragmentation. So now, middle down. So Aaron showed you that you can get nice data on the Q-exactive with middle down, but you get HCD fragmentation. And ETD for bigger peptide and proteins will give you, is more efficient, so you should get a little bit more sequence coverage. So when you do ETD, it's an ion-ion reaction, and you need to control a lot of the parameters. And one of the parameters is the isolation window. So you could decide to isolate just one charge state or 300 Dalton, and it's in a tune page, and you can set it up very, very easily. And because it's an ion-ion reaction, what's important is how much of these two populations of ions you are going to mix. And in that case, we have an AGC target for the precursor and the reagent, so you are in full control. And also, the reaction time is important because the longer you let these two populations reacting together, the smaller pieces you will get. So you want to decide what's the best reaction time for the compound you are analyzing. And finally, you also have access to supplementary energy. So now, when I do the acquisition of this data, my file name got crazy because I need to record all of those. So in that case, it was the light chain of Trastuzumab. It was a 300 Dalton isolation window. The precursor was at 3E5. The reagent was at 7E5. And the reaction time was 10 milliseconds. So another point that when we do middle down, resolution is critical. Because if we look at this like 80 M/Z window, this is what you get. There's so many ions. And even without the convolution, the Excalibur is able to pick up what is the charge state. So due to complexity of the spectra of top-down, high resolution is required. So I usually run all of my experiments at 120 and sometimes at 240 K resolution. So in that experiment, we actually did, so let me explain. So I changed the ETD reaction time. I look at the residue cleavages, how many bonds did I identify, and I use it as 2 parent ions AGC value, one at 3E5 and one at 1E6. And so when you do ETD, there's actually a lot going on. First, you isolate the parent in the Q1, and you are going to send it to the high-pressure cell. But if you look at the high-pressure cell, there's actually 3 portions, the front, the middle, and the back. And the one in the middle is the one with more space. So the way it was done on the fusion, you were sending the parent ion in the back and the reagent in the middle, and after that you are mixing them together. So this is why on a fusion, the parent ion AGC value recommended is 3.5. When we move to the fusion LUMOS, we recommend 1E6, and the reason is because now we're going to do a different way. We're going to trap the parent ion in the middle part of the high-pressure cell where there's a lot more room. And then we're going to trap the anion in the front part, and we're going to mix them together. So now, by changing the way we're doing ETD, we're able to get higher, we're able to use higher target value. So what does it mean? So if you look at, for the light chain FC and FD, in blue is the 1E6, so what you can get with the LUMOS, and in yellow it's what you could get with the fusion. You get already very nice cleavages with the fusion, but with the LUMOS, you get higher sequence coverage, and you get it on different reaction time, which sometimes could be useful. Also, what we looked at is when I select these 3 reaction time, and I match those ions, so those are the ones that correspond to cleavages for my sequence. When you use 5 milliseconds, the match ions are actually at higher mass. And when I go to 35 milliseconds, I create a lot smaller pieces. And what happens when you let reacting for a longer period of time, you will get smaller and smaller pieces. So this is why if you want to get high sequence coverage, you are going to use different reaction time because you are going to generate different type of ions. So if you put those together, you are going to increase your sequence coverage. So let me show you what you can get when you put 4 raw files together, so 3 different reaction type plus 1 ETHCD. On the light chain, you can get 70% sequence coverage. On the FC, 67% coverage. And on the FD, 60% sequence coverage, which is very high that you can get in just like 4 injection. And for each of them, I probably injected 1 microgram on the map pack column. So now we did the same experiment, but with the NISMAB in that case. And this is the ETD, and this is on the LUMOS, and it's just 1 run at 10 milliseconds. And in that case, on the light chain, I already got like 60% sequence coverage on the FC52 and the FD43. And also, we have another mode of fragmentation that's not commercial yet, but in the R&D group, I had access to it, so I did UVPD. And this is what I got on UVPD. So it's slightly lower than what I got with the ETD, but what's important is when I combine these two, I get very high sequence coverage in just 2 runs. And why? It's because the ETD and the UVPD, it's UV photodissociation, are actually complementary fragmentation technique. So actually, just in 2 runs, when I used add the UVPD, I got an increase in sequence coverage by more than 30% for all of the subunit. So the UVPD will be very, very powerful when it will be time, just when you want to have high throughput and don't run your sample for 4 or 5 times to get high sequence coverage. So now, last part, HDX. So HDX, it's most of the time an MS1 experiment. So you have your protein, you do your labeling at different time, you quench, you digest with pepsins, you do a very quick, at low temperature, MS1 separation, and you look at different time points, you look at how the envelope is going to move, and you can calculate the uptake. So why do we stay at MS1? Why we don't use the MS2? Because if you use MS2 with HCD, you actually will have deuterium scrambling. So the deuterium goes to one amino acid, but when you do MS2, they are going to move around, so you cannot pinpoint which one was occupied. So when you do at the MS1, you define a region where you have an uptake, a difference between a control. For example, when you do protein and protein ligand, you can find a region where the ligand is. But now if you would like to pinpoint which amino acid is the ligand on, exactly just to pinpoint, you won't be able to do it with HCD. So ETD is a fast mode of fragmentation, so can we do it with it? So the first thing you have to check is you don't have any scrambling in your source region. So the typical way to check for it is to use that peptide. And on the N-terminal side of that peptide, you have 5 or 6 histidines. Why is it important to have those histidines? They fast exchange very, very quickly. So when you do your experiment, those should not be deuterated. If you see any deuterium on them, they come from scrambling because they quick fast exchange in the solvent. So this is why if you look at the C2 to C6, you actually have just a slight change. That means you have minimum scrambling. But if you look at what you have right after, when you move out of this histidine here, you have the increase in deuterium. So this is how you control that your source conditions are correct and you can use ETD. So that figures, it's a protein ligand binding experiment. So you run your protein by itself, you run your protein with the ligand, and then now you are going to calculate for each fragment ions, the C and the Z. Because when you move along your peptide, when you have a deuterium on the peptide, it's going to move up. The mass is going to increase on your fragment. So what you were doing at the MS1 at the peptide level, now you can do it at the MS2 for the C and Z ions. So that figure is actually a lot of data because what that figure represents is the delta for each fragment ions between the protein and the protein ligand. And what you see here, this is more or less flat between from C4 to C3 to C14. That means there's no difference between the protein and the protein ligand. But when you move just after between the C14 and the C17, you have a huge jump. That means that's the way the ligand is, because when you have the ligand, now you cannot have the deuterium because the ligand will occupy that amino acid. So now you can see there's a huge jump between the two. So now you have amino acid resolution at the ETD level. When you want to do that with HCD, you can achieve something similar, but you will have to have a lot of peptide that overlap in the sequence, in the peptide digestion, to be able to pinpoint. Here it's pretty straightforward, and we get the same information with the Z ions. So in summary, ETD is a must-have type of fragmentation for in-depth characterization of biotherapeutic proteins. So HCD is very, very good. It's all around the best, but sometimes you will need to have another type of fragmentation to answer your questions. The middle-down experiment, now we get very high sequence coverage, so now we can use it to answer a question. It's not just an exercise, or can we get high sequence coverage? And finally, arbitrary fusion lumos offer multiple type of fragmentation and ease of use, and I think it's very important because there's a lot of analyzer on it, and there's a lot of experiments you can design, and the way the tune is done, it's very, very easy to use. Finally, all of that work, I interact with a lot of people, and I'm not going to name all of them, but this is a teamwork. Thank you very much.